This is problem 190 from chapter 12. We are asked to solve problem 12-189, but when the particle has an angular acceleration of 5 radians per second squared, when theta dot is equal to 4 radians per second and theta is equal to pi over 2. This figure here goes for both problems 189 and 190. In problem 189, we read that a particle moves along an Archimedean spiral. R is equal to 8 times theta in feet when theta is given in radians. We want to determine the radial and transverse components of the particle's velocity and acceleration, so that's what we're looking for in problem 190. And we need to sketch the curve and show the components on the curve. I don't really think we need to sketch the curve because it just looks like what they have here, but we will sketch the components. So the Archimedean spiral is named after Archimedes, who is a Greek mathematician famous for taking a bath and crying out Eureka. If you'd like to know more about Archimedes, you can come visit me in office hour and we will have story time with Professor Moore. So I need to find the components of the velocity and the acceleration. I have my equation for velocity here. I have my equation for the acceleration here. I have theta, theta dot, and theta double dot, and I have r, although I do need to take theta and plug it into r, so I guess we'll do that down here. So r is equal to 8 times theta. Theta is equal to pi over 2. So when we put that in, we get 4 times pi, and I'm just going to leave it like that for now. Then I need r dot, so remember I have to use the chain rule, take the derivative of r with respect to theta, and then take the derivative of theta with respect to time, which is just theta dot. So the derivative of 8 theta with respect to theta is just 8, and then I multiply by d theta dt. And theta dot is equal to 4 radians per second, so this is 8 times 4, which gives me 32. And then I have r double dot, where we take the derivative of r dot with respect to theta dot, and then take the derivative of theta dot with respect to t. And so taking the derivative of this with respect to theta dot just gives me 8, but then we have to take the derivative of theta dot with respect to t, and that gives us theta double dot. Theta double dot is equal to 5, so this is 8 times 5, which is 40. Okay, so now we're ready to find all the components. The radial component is just equal to r dot. R dot is equal to 32, and this has units of feet per second. The transverse component is equal to r times theta dot. R is equal to 4 times pi. Theta dot is equal to 4. And that gives me 16 times pi, which is 50.3 feet per second. There's 1. There's 2. Now we move on to the acceleration. For the radial component of the acceleration, I have r double dot minus r times theta dot squared. R double dot is 40 minus r. This is 4 times pi. Theta dot is 4. And you can plug this into your calculator. You should get negative 161. And then for the transverse component, that's r theta double dot plus 2, r dot theta dot. R is 4 pi. Theta double dot is 5 plus 2. R dot is 32. Theta dot is 4. And for this, you should get 319. Okay, and then we have to sketch the components as well. So what they're looking for us to do here is figure out the direction of the velocity, which, okay, so let's just do it this way. So it's kind of easier because we're looking at, well, I guess they had theta is equal to pi over 2 for problem 189 also. But because the angle is 90 degrees, we are right here on the curve. So we're at this point here. And the radial component, so radial is pointing outward from the origin to the particle, continuing up this way. So this is the radial direction. The transverse direction is perpendicular to that. So this is the radial direction. This is the transverse direction pointing in the direction of the increasing theta. The radial component is 32. The transverse component is 50. 50 is larger than 32. We don't have to get the proportions exactly right, but let's say something like this is 32. This is 50.3. So the velocity would be pointing roughly in that direction. Okay, now we're going to do something similar for the acceleration. This is the radial direction. This is the transverse direction. We have negative 161 for the radial component, so that would be pointing this way with a length of 161 feet per second squared. 319 is larger than that. I'm not going to get the proportions. Well, I'll get them roughly correct, hopefully. Okay, and then we add them together, and we get our acceleration vector pointing something like that. So velocity is pointing in the second quadrant, acceleration is pointing in the third quadrant. I think that's all they were looking for there. So that concludes problem 190.